My pleasure to introduce Shawn Frayne. He's going to be talking about the Windbelt. This is like an awesome in the coolness factor. So without further ado.
Thanks, Caillou. Really excited to, is this too loud? Okay. I'm really excited to be here today. I was at a talk a few months ago, and there's a, I don't know if you all were at his talk, but he's a professor at Harvard who's doing microbial fuel cells, basically turning chicken crap into electricity, you know, the coolest thing in the world. And I said, wow, Peter, how's that going? And he said, it's going pretty well. I'm giving a talk at Google. So, I'm really, really excited to be here. The company I'm going to be talking about and the technology you're going to be talking about today falls under my startup, which is Humdinger Wind Energy. And our focus is a new type of wind generator, which is the first viable non-turbine alternative to turbine-based systems. And I'll dive right in a few minutes into the technology itself and let you guys kind of poke holes in it and ask questions and whatnot. But I wanted to warn you that my goal in coming to this talk is twofold. One is to talk about the technology. It's called the Windbelt. I'll show you a little demo. And to get your feedback, because it's an early stage technology that's really just starting to crawl out of the water onto land. So any input's most appreciated. But my second goal is to talk a little bit about this design and invention movement. It's sort of where Humdinger Wind Energy came out of and where the technology behind our company came from, and that's focusing on technologies developed specifically for developing countries. And then seeing how, the interesting thing that's happening is this field of appropriate technology or design for developing countries is changing. It's no longer the technology that's in Uncle Ned's, workshop in the backwoods of, Wisconsin. I hope no one's from Wisconsin. But it's changing into the most cutting-edge technology, because when you give yourself the most difficult constraints in the world, which you often find in developing countries, sometimes, and other folks are finding a lot of times, that yields new patentable technologies which can have play in markets other than the developing countries. So I'll get into that at the end while you're held hostage here. But just jumping right into it, so first, something you guys know. What is this? No, I'm kidding. It's wind power up to date it can be summarized by a few words: something that spins. And I don't mean that in a derogatory way. That's just the way it is. You go back 2,000 years to look at when wind power was first starting to be harnessed, and you see things. You see spinning windmills that would pound grain, and then a little bit later you would see spinning windmills that would pump water, and more recently, in the last 100 years, there's been a lot of research into wind turbines that spin, focus in a large area of wind to a small gearbox, spin up some magnetics and some coils and whatnot, and then get efficient electrical output that way. That's great, and that works really well on the very large scale when you have a vast area of wind that you're concentrating down. But when you start to scale down wind power to the sub 100 watt field, that turbine technology, that focus on rotational systems, no longer is viable. And that's why there's nothing on the market presently in wind power in these very small, sub 100 watt ranges. You might discount that and say, well, who cares about sub 100 watt? But if you look at photovoltaics, a very large percentage, by energy about 7 or 8%, I believe, of the PV market in the world are these very, very small scale energy uses for powering all sorts of small scale apps. Wind power just doesn't have that for a variety of reasons. When you scale down a wind turbine, the percentage of losses you get in your bearings becomes a higher percentage of your overall power output. You don't have the same angular momentum that you have on the very large scale. So the dynamics change a lot. So that's why no one's been successful at scaling down wind turbines. So the way that I got into this and what led to the formation of Humdinger Wind Energy was a group of new constraints. And just to give you some background, this is a shot taken from the roof where we were installing some solar panels from BP at a fishing village in Haiti, Petit Dance. And I've done some work there for the last 4 or 5 years. It's a group out of MIT that works with a few different organizations in Haiti. We were doing things like converting agricultural waste, such as what's left over after you squeeze the juice out of sugar cane, converting that into cooking charcoal with very low-cost technologies, focusing on things like solar water disinfection. While I was there, I also realized, which a lot of other folks have realized as well, that kerosene lighting is the predominant form of lighting for a lot of homes. And when you use kerosene, kerosene is an outdated fuel for lighting, to say the least. It's inefficient in terms of energy input and light you get out, but it's also dangerous, hazardous, and costly. You can spend $5 to $10 a month on kerosene fuel just for a couple of lamps. So all those things combined led me to want to focus on a system that all in, these were my constraints, that all in would cost about $10, provide power to a couple of white LEDs. You might have read about a lot of groups coming out of Stanford and MIT and whatnot that are forming startups that are looking at how to displace kerosene with white LEDs. The problem is there's a missing component to their system, and that's the very micro-scale power component. So my goal was to design a wind generator that would contribute to this system, the system all in, including wind generator, batteries, power conditioning unit, and a couple white LEDs that would be around $10 cost. I tried to do that with turbines, and it turned out to be way, way off by a few orders of magnitude. So that forced this new invention called the Windbelt. And basically I guess our motto at Humdinger is that harder problems make for better inventions. So by giving yourself really difficult constraints, you can come up with something new that maybe you couldn't come up with if you didn't have the tight cost constraints that you would have in this case in Haiti. Some of those constraints, just to run through them, like I was saying, whole lighting system all in about $10. Let me just see this. Let's get a look at the time. Whole system all in about $10. So the wind generator component of that would be about $5 max cost. Can be manufactured in Haiti. That was another constraint. It's very difficult. Those panels, that picture that was taken off the roof with those solar panels, those panels took about 2 years to get into Haiti. They got stolen in the port. We were waiting by the panels, and they were covered in a blanket. And someone, before we hopped on the little puddle hopper to get to Petit Dance, pulled back the blanket, and it turned out someone had switched the panels for a table. And so we got them back. But needless to say, it would be good if there was an energy system that could be manufactured in developing countries. And I'm going to get to some of the, I'm focusing initially on where this technology came from, but I'm going to get to where I think it can go. And there's a lot of other markets in wealthy countries like the US, countries in the EU, Japan, that can benefit from this technology as well. But, just keeping on target here, another set of constraints was no specialized materials. I didn't want a system like a solar panel, nothing against solar panels at all, but I didn't want a system that needed to have a silicon processing infrastructure built up or have to have a special material imported. It's just, it would make it easier to get the product off the ground. If magnets were necessary for this wind generator, they needed to be small. There's a lot of import restrictions on larger size magnets that you would use for a traditional sort of homebrew wind system. One of my friends in Guatemala was telling me he can't get these large super magnets imported in at all. So you need a set of magnets that's small enough, that produces a small enough magnetic field that you can easily case it in with just a steel case and then ship it without any import restrictions. And easy to repair and improve. Part of the objective was to design a technology that would be, viable when it hit the markets, but would be able to be transparent enough and easy enough to fix and easy enough to improve that the technology could be developed kind of in-house. That is to say, engineers and inventors in Haiti could improve the technology, sort of going for the open source hardware idea, but with power. So, the final constraint was I wanted to minimize the grinding in wearable parts. This is, basic fundamental principle that I think everyone tries to achieve. So I really wanted to eliminate any bearings in the system because when you're down at these sort of small scale power levels that power things like LED lights and radios and charged cell phones, you need pretty expensive bearings, air bearings, to make a viable system. I didn't want to deal with that. Too expensive, difficult to repair, difficult to import. So that was another constraint. All these things led up to forming an invention that, in a caricature looks more like this, a stringed instrument or the vibrating bow of a musical instrument, you could say. So as opposed to wind turbines, which are basically a big rotating airplane wing, a big rotating airfoil, the technology that we came up with after looking at those constraints looked more like the vibrating bow of a violin, let's say. So what do I really mean by that? What I really mean is that we're focusing on a different phenomenon with this new technology. Lift and drag is what governs sort of the operation of an airplane or a turbine. But there's a lot of other aerodynamic phenomena out there that you can tap. The one that we ended up tapping looks pretty familiar, I think, to engineers and anyone who's gone through middle school in the States, I think. And that's the Tacoma Narrows Bridge. The effect that ripped apart this bridge is called aeroelastic flutter, sort of a positive feedback loop of competing forces of lift versus the tension forces in the bridge. Usually, you try to minimize or eliminate aeroelastic flutter from any aerodynamic or structural system. So there's a lot of work that's gone into how to eliminate aeroelastic flutter. But if there was a way that you could control the forces involved and control that effect and harness it for energy output, then that would be a viable alternative to lift and drag over an airfoil. Wind power's a few things. We were talking about it before the talk. I see wind power as a few things, three main goals. One, you have to collect, just like a magnifying lens, kind of, there's these new solar panels that have come out which have optics that focus in a larger area of sun into a very small, high efficiency little PV panel of sorts. I don't even know if PV panel of sorts. The goal for wind power is the same. You want to focus in a large area of wind into a smaller area. Then usually you have to do something with making that small area move at a high enough frequency that you can get an efficient electrical output from magnets moving past coils, by and large. And then the third thing is you need to condition that power. What the Windbelt does, what this new technology does, is it looks at new ways to tackle one and a little bit of two. How to concentrate in an area of wind for efficient electrical output and different sorts of configurations of magnetics and coils and whatnot. And we did have to make some very inexpensive power conditioning units to take care of our cost constraints, but that wasn't the main focus. Just keeping an eye on the time. And if there's any questions, just holler them out during the talk and we can get more down to it at the end. Okay, so that was just to remind me that wanted to not wait too long to show you the demo because that'll kind of give you a better idea of what it is I'm talking about and I won't be so vague. But I wanted to give you a little bit of a background of where this came from so that you'll understand where I think it can go and also so that you understand why it's so different from other wind systems out there. So just to stop any the comment I get most from engineers is, oh, that's great, you can charge a cell phone or you can power a couple LEDs, but you're pulling in 70 watts into your fan and you're getting out a fraction of a watt. That is true, but it is not my fault that the fan is inefficient. There's about 3 to 5 watts of power coming out in this large cross-section at about 10 or 11 miles per hour, which is what the demo is I'm going to show you right now. And we're cutting a sliver of that. So efficiency all in ends up being around 10%, when you take into account the losses through the power conditioning unit into a matched load. Just to stop that question in its tracks, but feel free to ask me if that didn't convince you.
We're going to ship the fan to Haiti also?
So this is just the first demo of a couple. So this is to show that this system, which again is just a demo system, but that this system hit those constraints. A couple white LEDs, just to show you there's no magic going on here. Show you that it works at a few different speeds. This is around 11 miles per hour. This is around 8 miles per hour. I'm showing you the different speeds because a comment that I get often is, oh, well, that's a great idea, fine, but you have to hit 11.2 miles per hour to get the resonant effect. But this isn't, there's resonance involved, but the Tacoma Narrows Bridge was not ripped apart by the same forces that let the opera singer blow apart, the wine glass. So it's not that you're having to hit a specific frequency. It's more of a, resonance is a kind of positive feedback loop too, but this is more of a positive feedback loop of competing forces. So that is to say, you can tap a wide range of wind speeds without having to have a dynamic tensioning system, although that would be nice. So let me show you another demo just to show you that it can do everything I said it could do. So if there's any questions while I'm doing this, feel free to shoot.
So what's your power conditioning doing right now?
So that's the only thing I can't talk too much about because the patents still haven't been fully filed. But the power conditioning unit, you're getting in a very clean AC input, and you need to do a few things. You need to rectify and you need to boost. Typically, you would do that with something, like boost converter, in combination with, a typical bridge rectifier. The cost was too high for those two things combined, and the losses were too great. So so all I can say, especially since this is on tape, is that there's a few components that you could pull out of, any old radio that are in the power conditioning unit. And quantity cost is probably somewhere around, 25 cents or 50 cents. So they're standard components, no kind of silicon components in there.
What wind range does this unit operate at?
This unit operates at between around 4 miles per hour when it starts to put out power to around 14. Actually, this one probably to around 12 or 13, but we've had systems that work in that range. After 14, it's not that your system just kind of falls over and dies. It starts to hiccup and go ahead of itself. And what we're finding as I look at kind of larger scale systems is that that's sort of a function of this particular size. Working on systems now where this effect seems to give increasing power levels through a wider range of wind speeds.
So as you change, so what on the table there is vibrating? Is it that slim bar across the top?
It's actually just, and you can get a closer look afterwards, but it's just this band here. It's a band of, it's kind of it's a mylar-coated taffeta. It's a very, very, very primitive sort of composite material that is very commodity. You can use it for things like the edging of kites.
And as you change the wind speed, does that change the vibration frequency, or does it change
It does.
the amplitude?
It does change. Mostly the amplitude, but the frequency changes by a few hertz.
All right.
It's going at about 100 hertz now, so that's why it's giving some efficient output. This is to show you that it can do the duty cycle of charging a lithium-ion battery in a phone. It would take a long time for this particular scale to fully charge up the phone. I don't know if you could tell the difference as I was talking over it, but the initial startup is very difficult for a system that's as gossamer as this to do. So it took a while to be able to design a system that could actually get over that initial part of the charge cycle. Then one more, and keep shooting out questions as I do this.
How long would it take to charge a typical cell phone?
Off of this system right here,
A few days.
like a week. But we've charged it up. We've let it run for a few hours and have made half an hour's worth of calls. So it's more of a demo.
What happens if it's rotated a bit?
Oh yeah, okay, I can show you that. Let me show you that right after this one. But it works, it's the same sort of sinusoidal fall off that you would get from any change in cross section, approximately. So, a wind turbine, you get that kind of fall off as your cross section changes, similarly with this system. But I'll show you to convince you this. So this is a crank radio only because crank radios require very little power. This may or may not work. I haven't tested it. This is at the very edge, powering a speaker that people can hear. It's at the very edge of what this system can do, but I figure what the heck. Okay. Okay. So people just like that because it's like, literally showing, that we're hitting about 4.5 volts to replace the few AA's. So there's that one. I'm not going to get into too much the business side because I know this is a tech talk, so that's why I'm just kind of not too worried about screwing around with the demo here with you guys. So I hope you don't mind, but so let me show you this. So I don't know if you all can see the LED there. This system's on its last legs. This is the last demo it has to go through. It's kind of been around the States a dozen times, so the baggage handlers haven't been kind. I have a big note that says, this is an experimental wind generator, but they open it anyway. I think that makes them open it. So this is to show you that unlike most turbine-based systems, this can take pretty smooth laminar flow, which this is pretty rough and tumble, but it can also take really, really screwed up non-laminar flow from my breath. So I don't know if everyone can see that, but that's just that part of the demo. So that, if you're interested after the talk, I can show you these are all sort of the developing country applications. And after the talk, I can show you, if you're interested, kind of on the side, how this system powers a wireless sensor node, which is one of the key first kind of killer apps for the Windbelt in wealthy countries. Namely systems that you could have, imagine a peel and stick flat Windbelt that was about yay long, about yay wide, and about yay high. That would put out just a milliwatt of power. But then that's enough, combined with a buffer like a capacitor, to power up a lot of wireless sensors that do things like report temperature, report humidity, things that you need in any smart building to be able to make a more intelligent heating and ventilation system, because that's where about 50% of a building's energy flows. So to make any sort of LEED certified or green building, you need to know what's flowing through the ducts. Right now, that's difficult because these sensors all require batteries, and you can imagine needing to call it Tom Cruise to crawl through the ducting system to replace all these batteries every couple of years when you need a few hundred to 1,000 sensors throughout the ducting of a large building. So I can show you that afterwards, but there was a question.
Yeah, I could, and maybe this would be correct or not, but I could describe this as a device where the working fluid is air. Yeah. But if you were to replace that by something, this thing ought to work underwater, right?
So I can't say that it can or can't. It's conceivable. The effect is still there. The thing is, I have to be a little vague. I get a lot of inquiries about whether or not aeroelastic flutter works in different fluids, such as water. My personal opinion right now is that there are other effects that are maybe more viable in kind of constant flowing water. If you're interested, there's a group, I think out of Colorado maybe, called Vortex Hydro Energy that uses vortice shedding, which is basically little whirlpools that spin off of a cylinder. And because your water is so much denser than air, vortice shedding kind of makes that cylinder move up and down with a pretty good amount of force. And you get dead spots because vortice shedding is a periodic. It makes something oscillate at a periodic frequency, so you get dead spots. That's it. So I guess what I'm saying is, in air, there's no other system that competes with this sort of model at these scales. We're about 10 times to 30 times more efficient than wind turbines that are on this scale. So that's important. When you go up an order of magnitude in terms of cross-section that's cut, we become much less efficient. Not much less, but less efficient than larger scale systems. But there was a recent publication about a couple years ago in Nature about a small scale turbine, and we're about 10 times more efficient than that. And they put out a new study, and we're about 30 times more efficient than that one. But these two questions, and then we'll save the rest for the end.
What last legs is it on?
It's I can tell that the frequency's changing a little bit.
So like what's failing is what I'm saying.
Yeah, I'm not exactly sure. We've put the systems through 200 hours of operation in the lab, just kind of constantly going through different kind of heating and cooling cycles, throughout over the period of a couple months. And it seems as if the frequency stayed roughly the same, and the power output was roughly the same. With this one, I can tell that there's something out of alignment, and I can hear it. So it's not that, I think maybe there's just some misalignment that's happened up on this end.
What happens in a hurricane? I think you said that was made out of mylar. I think mylar will stretch unless you've got some carbon fiber.
It's a mylar-coated taffeta, so mylar alone isn't good enough.
Yeah, right. So that's probably what's failing here. But what happens in a hurricane? And if you want more power, do you make a lot of little ones or do you make a bigger one?
I'll answer that at the end. And what happens in a hurricane, I think there's going to probably be some questions about dynamic tensioning. So I'll buzz through the next bit just so that there's enough time for questions. Sorry, I don't have a watch, so I have to keep looking up there. Just to show, this is what I just stated, and if you want to look at the reference, I got a lot of flack for people thinking that I was saying that the Windbelt is 10 times more efficient than wind turbines, which would be impossible, wind turbines on a large scale. So I'm being very specific now, and you can check out this citation at our website, humdingerwind.com, and do the comparison for yourself. We're comparing the cross-section that's cut by the Windbelt as it oscillates, and tagging that against the cross-sectional kind of area of the wind turbines that are published. There's very little data in this range for wind turbines because a lot of the stuff that's out there, it's about 1,000 times less efficient than this sort of system.
Don't you have to measure the cross-sectional area of the entire aluminum frame? Because, I mean, that's going to have effect.
Yeah, so in this system, there would be an argument for that, but I can actually remove this top bit, and there's no sort of funneling that's going on. Part of what I've been mentioning about the strategy of Humdinger wind energy isn't, for a long time I didn't even mention the whole developing country aspect of it because that confused some people, or I thought it would. Now I hope it doesn't, but the purpose, the reason I mention is because that's where the technology came from, and that's why it's so different. But that difference doesn't mean that it doesn't have applications in wealthy countries, which I believe is a powerful phenomenon that's going to happen in a lot of other fields as well. I mentioned one sort of application, which is these small peel and stick, little peel and stick energy harvesters instead of batteries wherever you have an airflow. There's other applications as well, which I'll get to in the next slide. But the idea is there's there's IP in this. And if that IP can be licensed in wealthy countries, it still stays open source in developing countries just by the nature of the patent system. There is no international worldwide stamp of approval patent patents are by country, so there's no reason to patent something in Haiti. So it's still open source where I want it to be open source, but it's protected where I think some licensing revenues can be pulled out, and then the ultimate objective, through me, I'm not the only one in the company, but the revenues that flow through me flow back to the original objective, which is these emerging economy markets. We're not a social venture. It's a hardcore, regular business in Silicon Valley, but it's just something that is an aspect to it. So that's just what I was saying. Next steps on the horizon. What we're doing is exploring the landscape of where this technology can go. There was a question about scale, and hopefully this answers it a little bit. I already mentioned these powering very, very micro-sized systems, and there's really nothing else in the game in terms of using wind power to power very small scale, sub 1 watt applications, and there's a lot of them out there. However, the question, seeing this system will also, I think, get a lot of people thinking, and it has, on what happens when you scale up a little bit. Let's say you scale up to a 1 to 10 watt system. Based on the bill of materials, and we're just in initial testing for this scale, it seems as if we'll be able to achieve around a 10 watt system, and that's rated power, so it would be 10 watts at around 22 miles per hour. So basically a 1 to 10 watt system. A 10 watt system for cost bill of materials around $10. If you compare that to what wind energy costs on the large scale, that beats it in terms of cost per watt. A lot of people discount this, out of hand. But when you look at the number of components that are involved in this Windbelt system, then I think people will start to come around, and pretty soon we hope to have a demo model of this size scale system that hits these goals. These are good for things like rural electrification in, let's say China, where there's not much solar irradiance in certain areas because of the pollution. So your solar panel, which is $5 to $6 per watt, suddenly when you have 100 times less solar energy hitting that area of the panel, becomes $500 or $600 per produced watt. So it becomes non-viable. But in some of those places, wind is a viable input. Also things like Wi-Fi nodes. I know they were trying to put up Wi-Fi nodes in Central Park. And they were having a big cost issue with wiring things up there. So having these small scale systems that use wind and maybe in combination with solar to power apps like Wi-Fi nodes and rural electrification, I think is one part of the landscape. And another big part of the landscape is how big does this thing scale up? Anyone who knows anything about scaling up anything knows that you cannot make claims out of hand that something scales, because the dynamics on the large scale are different than the dynamics on the very micro scale. Turbines have found this to be true. So similarly, we may have an upstream, kind of a battle going uphill. However, it's unknown. We know the effect is present because it rips apart things on the large scale. The question is, can we make an efficient enough generator on these large scales to hit the price points we need to make that a viable alternative to turbines on the large kilowatt plus scale? And that's a big open question, but it's part of what this next year of development is intended for. Part of the plan, part of the kind of non-conventional plan is, because it's difficult to do large scale test installations in the States, partnering with an organization, and I encourage everyone to check them out. They're AIDG, Appropriate Infrastructure Development Group, based out of Guatemala, but also with operations in Haiti, so AIDG.org. I'm not affiliated with them now, but they're going to be a partner with us in exploring how the Windbelt scales up to these large kind of stretch across a canyon scales. And I think we're going to get there faster, and we're going to get there, not to sound like NASA, but I think we're going to get there faster and get there cheaper than we would with domestic resources devoted towards, having an R&D center in Silicon Valley, for instance, for these large-scale systems. So that's one tier of the experiment. How am I doing on time here? Okay. So now that I've gone through the Windbelt, you're going to have to bear with me for another 5 minutes as I kind of poke at you about this coming design revolution, which Humdinger Wind Energy is a part of, but which a lot of other folks are starting to pioneer. And I see this as something that isn't on a lot of folks' radar. So I'm sort of the West Coast evangelist for this new design revolution as I see it. So the basic idea goes along with what I said at the beginning of the talk, and that's that harder problems make for better inventions. The hardest problems in the world happen to be in developing countries by and large. They're kind of the avant-garde of the problems, you know. Clean water, energy, all these sorts of things are going to impact, you know, in 10 to 20 years, and they're already starting to, they won't only be severely impacting developing countries, they'll be impacting everybody. So the technologies that are developed now, which focus on these very difficult constraints in developing countries, are going to have crossover. And I think they're going to have crossover in several fields. You know, I'll just buzz through this so there's plenty of time for questions. These are just some of the fields that I think there haven't been the advances needed over the last 50 years that need to happen. If you look back 100 years ago, when a lot of the kind of foundations for the technologies we have today were made, you know, Edison and the light bulb and electricity and dynamos and whatnot, the reason those were developed is that the entire world was a developing country. You know, the entire world, every country in the world was a developing country, except for a very, very, very small, tiny elite. So the designers and inventors at that time were very well wed to the problems of the day, whereas now, about 10% of the world that does most of the design is disconnected from the other 90% of the world. And I think what that does is it loosens kind of the vice grip of constraints and makes for poorer design. And you know, you get to a point and you say, okay, that hits my constraints. And then there's these legacy effects that come into play where an average design gets kind of carried through decades. Now what needs to happen is that the new industry starters need to be developed, just like happened 100 years ago. You know, obviously I'm not talking about the internet because that's a recent phenomenon, but besides that, for things like power and whatnot, I think the place a lot of this is going to come is from developing countries. And there's going to be, as Jeff Immelt, the CEO of GE said, this is sort of going to be the third phase, the third stage of globalization, where inventions and developments in developing countries are going to affect the developed world in ways that people don't see. I was very surprised to hear him say that. But just some examples of places that this revolution has already begun. I know that everyone here, I've seen all the posters for the give one, get one $100 laptop all around Google. But what's cool to me, besides that sort of strategy of give one, get one, is the screen. So this was a technology that was developed with very severe constraints, you know, very severe power constraints. You had to make a laptop that was, you know, it consumed a 20th or a 10th the power of a traditional laptop. You had to make, and you know, the screen consumed a lot of that power. So what these guys did was, and not, I think the inventor was expert in display technologies, and I think she's out of MIT, I'm not sure, but what she did was designed pixels, regular kind of luminescing pixels that you know, work like a regular screen when you're in the dark, but then you can switch it into more of an e-reader mode, kind of like an e-ink type of, it's not e-ink's technology, but an e-ink type of reflective display that doesn't consume power when it doesn't change state. And I want that on my laptop. But it's in these $100 laptops, and the only reason that it's there is because of these severe power constraints and the constraint of needing to be able to read your laptop in full sunlight. So I think that's something that's going to cross over and was only developed with these constraints. I'll buzz through these other ones, but it's important that this next organization, Japper Foot, is super interesting. They're designing prosthetics in India that are, you know, 100 times less expensive than prosthetics in the States, and they've developed some interesting molding technologies using basically sand in a vacuum, sort of a vacuum bag. They pull the air out, and you can make kind of instant molds of a person's, you know, person's limb that that's been amputated. And then you can make these customized prosthetics. Importantly, even more importantly than the cost, is they can do this in a 1 to 2 day turnaround time. Whereas in the States, someone coming back from Iraq has to wait 6 months to get a prosthetic limb. And this is something I see possibly crossing over as well. They just won a tech award, so you can read about them there. Inexpensive cars because of the cost constraints in India, phase change incubation. Amy Smith out of MIT has developed a new way of incubating biological samples using a phase change material, which is basically a wax that you heat up to, you put the wax, little balls of wax out in the sun. It melts the wax. So by melting the wax, you're absorbing the sun energy, or you can boil them. As the wax starts to resolidify, it lets out the temperature at its phase change, so around 37 degrees Celsius, and you can get constant temperature incubation for things like water and blood samples. This is something that I think is going to affect medical technology in a lot of realms. And again, developed with these constraints of not being able to have a $2,000 incubator that you need to recharge before you go out into the field. And the Motophone is pretty cool. It uses kind of an e-ink style display. I think they're $30 retail. The power, it can, I don't remember exactly what the duration is, but it's something like 200 hours of, I don't know, you have to look it up, but it's almost an order of magnitude more talk time and standby time than the phones that you have in your pocket right now. Just because, again, of power constraints. You go to the city once and recharge your phone, you don't want to have to keep going. So don't quote me on that order of magnitude greater, but it's substantial. And I guess that's it. Oh, the Windbelt, right. So I guess that's it, but more than the technology itself, which, I'm a technology guy, so I love the technology of the Windbelt and these other technologies. But more important than that is that there's this new system of invention and design that I think is coming to a head, in which a lot of the world's problems, including energy and clean water and poverty, are all going to coalesce into a lot of designers and a lot of inventors who focus on the problems in developing countries, with the outcome being that those aren't only a social charitable venture, that those yield patentable, protectable technologies in the developed, wealthy world that can then form industries the world over, not just developing countries. So, thanks. Any questions?
For the big scale, have you thought about using a bridge to stretch out a island?
Yeah, when on the large scale, it makes no sense to have a structure that beams, you don't have to hold the mountains from coming closer to one another. So in that case, you cost reduce by eliminating the structure, which in this case is, about half the cost. Obviously wouldn't be made out of aluminum, but yes, I guess the answer to the question is, on the large scale, the way to do it, I believe, is by grabbing onto existing structures, whether that's mountains or whether that's components of a bridge or architectural components, like in a frame of a window, let's say, and doing it that way. So, but again, I have to stress that there's been no testing on this vast scale, so all of this is, it's a postulation that it can scale up. But
Is that like the ideal place for the magnet? Why wouldn't you want it to be like more towards the middle to have other samples? Does that just affect the
it wouldn't. So if you did that, you'd get caught in more of a torsional mode, which is way, 100 or 1,000 times less energy output than this mode where you have this flutter of the membrane in the middle, and then that concentrates that sort of motion across this larger cross-section to the most massive part of the system, which are kind of those button magnets. So it works kind of like a flexible lever, you could say. So instead of getting your high-frequency oscillation of a magnet with reference to some coils by using a gearbox, instead you use, so instead of gears as your simple machine example, using leverage and getting that high-frequency output that way. Yeah.
So on that scale, really not audible that it's generating energy. It's hum a little bit. It's great.
Yeah, thanks.
But I'm thinking when you scale that up, you're going to run into issues of sound being generated by the.
That's one of the primary technical hurdles as it scales up, definitely. And I've scaled it up to around, a human-sized generator, which is kind of in this, 10 to 20 watt size system. And sometimes I can design the system to produce low levels of sound, but sometimes it's loud. Noise is lost energy. So the hypothesis is that with more attention to how the membrane's actually designed and tensioned, then we can get around that problem. But it's a definite concern. I think there was another, and then I'll get back.
Wondering if the frequency goes down as you get. Is that approximately true?
Approximately true.
So if you had a bridge size, it would be.
So I should just say, this prototype was designed months ago. So the new systems we're working on have a whole different dynamic than this system. This is one of the least efficient configurations for coils with reference to magnets, but it works at the wind speeds I needed it to work at. When you can have cut in at 8 miles per hour instead of 4 miles per hour, cut in, when you can have your wind generator starting to produce power at 8 miles per hour, then you can use a lot of other approaches, cord coils and whatnot arranged differently, and then your tension changes. But in general, that is probably a true statement.
You can also change the aerodynamics of the belt itself, right? I mean, just like a wing is different than a flat piece of paper. I mean, you'd want to do the same thing. Have you guys invested that?
I have not investigated it, but it's definitely something that has been on the radar for a few years. This has been in development for about 4 years,
I'll definitely send you the robot guitar.
Okay, yeah. There's a self-tensioning guitar that Kaya was telling me about. So, but designing a different sort of airfoil, which is I think what you're asking, having the membrane have that sort of different cross-section is definitely an area I think that we're going to investigate, and I think some other folks, once this catches on, will investigate as well.
Are you sticking with a mylar material for your other experiments, or do you fool around with other materials?
Yeah, we fool around. The thing is, it's very much in an Edison mode right now, where it's very empirical. Everything's empirically determined, because this phenomenon, even though it appears simple, is extremely difficult to model. There's still debate actually about why the Tacoma Narrows Bridge got ripped apart, if you can believe it. But it's extremely hard to model, so we just have to try a lot of things. And that's why I think doing this experiment in Guatemala is a way that we can actually be able to tap a wider range of fields and get the landscape clear more quickly, and then I'll come back.
What about the width? Have you played around?
Oh yeah, this is, for this scale, for this particular scale and this arrangement of coils, this is what I found to work the best. And if you diverge from that, even a millimeter, it changes the dynamics a lot. A millimeter's pretty big, but everything's handmade, so everything is within a millimeter.
So, to what extent, or do you even know, does the smoothness and the surface composition of the fluttering material interact with the wind and the speed and the frequency and all that? So this mylar is probably pretty smooth, right? But I would imagine that the same geometry with a different surface texture would probably behave differently.
Yeah, I believe so too. Actually, this material is smooth on the top where the mylar is coating the taffeta. So different materials do perform differently, and we haven't quantified. We don't exactly know why that is so. I mean, you get different flows along. Very, very smooth material, you're going to get more drag than you would get for kind of with kind of micro bumps. So all of these things have to come into play. I mean, what's important to realize is, even though I think this development can happen on a rapid scale, turbines have been in development for 100 years. The hope is that this can be, an order of magnitude less development time than that, but it's still crawling out of the water onto land. So most of these questions are unanswered, and the reason for the talk is to kind of get those questions going and get people thinking. How's the time? Am I interrupting another talk?
No,
okay.
I think we're...
Okay. Yeah.
So you've seen these turbines that they're usually vertical and they spin sort of this way, and there's a couple different blade configurations, but the advantage is that if the wind changes, comes from any direction, they still work. Now if you had one of these things, wouldn't you want to make it movable so it could track the wind? And it seems to me that there'd be a crossover point where there's got to be a crossover point where if you scale this up to some number of watts, right, and then you look at one of those small turbines, like the vertical spinning pole thing that I just had in mind. There must be a crossover point where that might start to look, that effect might be working a little bit better than whatever you could do with this.
Yeah. Again, it's not only it's all about the cost to me, because it doesn't, if you're out in the field somewhere, this particular generator can't take flow from both directions, but the larger scale generators can take flow from both directions. So you would get if you didn't have two coils perpendicular, you would have to have some sort of rotating system.
Yeah, we
but
could put a fin on the top.
Conceivably, but if the systems are so cheap to make, adding that bearing and ability to rotate on the small scale, the 10-watt scale, I believe is going to be more expensive than having two belts. However, there is going to be this crossover where it makes more sense to invest in that sort of system, vane system. I think you were next. And then.
Can you say a little bit about where the cost breakdown is? What fraction is the magnets versus?
Oh yeah, on this scale, each magnet costs about 5 cents quantity. The coils, not wound, but the cost of the copper in the coils in wire form is around 30 cents each, roughly. This would be made out of some sort of, probably ABS or glass-filled polyethylene, and for this much of that material, it's less than $1 in quantity, and then the material itself is probably a penny. This is some of the material here. And you can buy it in rolls. So the part of the system that could break is actually the least costly. So that's, I think, a good way to design a system, particularly for environments where you can replace that component.
Yeah. So on that scale, it's actually very easy to adjust for direction. You just have to have a fin on the end that sticks out and hang it from a wire.
Yes.
It's very simple.
Yeah,
it's not.
I think people are going to do that option. Conceivably.
Yeah, let gravity deal with the
Yeah.
rotation, right?
It's a good idea.
What about a funnel? Have you experimented with funnels into it?
Funneling works for. It'll work for a wind turbine too, but the problem there is, where you have to build a stronger structure to handle the drag that is forcing back that funneling. With this system, one of the advantages is that you don't have a big spinning, dangerous mass. So I don't have anything against turbines at all. I think people should get them, and I'm glad they're working on the large scale. But you do have a rotating mass, which you have to account for when you build the structure that turbine's on. Whereas in this, your mass is very, very, very small. The most massive part is close to the base. So you can have a bamboo pole, a thin piece of bamboo that holds up this system as opposed to a proper tower you would need for alternatives. And adding a funnel kind of reduces that benefit. However, I'm sure people are going to look at it.
Is it the power output some function of the mass?
Of the
magnets and the
belt
coils.
itself?
Of the magnets and the wire and the,
Yeah.
in other words, you're getting power from moving parts, right? So,
Oh yeah, it's definitely, it's a function of the frequency, roughly the mass, because the mass affects the field produced by a permanent magnet, and the area that, that field can influence. And those three factors, like any generator, that's what determines how much output you get. So what we're looking at is kind of how to focus in an area of wind to make those magnets move, which is the challenge for all generators.
Right, but it doesn't take very much. And the advantage, if you do channel a little bit of wind, you can get a slight Venturi effect, so you'll get a little bit better efficiency out of less wind.
No, I think that, so there's vast, that idea. I think there's vast improvements to be made. And I'm excited to see how fast this technology develops.
Yeah, it's awesome.
Thanks.
We're running out of time, so if you guys have more questions, you should join us at Charlie's.
Sure.
Thanks. Thanks.